Professor Helen Caines from Yale University. She graduated from Birmingham University, England, and she was working on strangeness production at the SPS Energy. Then she moved to Ohio State University as a postdoc, joining STAR, the BES collider experiment. And after a few years, she joined Yale as a faculty member. She was a co-spokesperson during 2017 and 23 with Zhang Bu and Li Juan. She's one of the strongest proponents for the beam energy scan program at the very beginning, and she holds the CPOD 2022. Currently, she is a member of STAR, ALICE, and the EIC experiment called EPIC. Today, the title is Beam Energy Scan 2 Physics, as you can see, the current status and the future outlook. Helen, please go ahead, start your talk.
Thank you. Hopefully you can hear me. So
yes.
I've got my slides in presentation mode, of course. So if you want to interrupt me, please just interrupt me. I can't see raised hands, but you're welcome to ask questions as I give the talk. And I know there's plenty of time by the organizers set aside to discuss afterwards. So I want to emphasize that although I'm talking about BES-II physics, which basically means I'm talking about STAR results, I'm talking on my own behalf, not from STAR. And I'm going to focus on new results that have come out mostly over the summer, but I will still can't cover it all in the hour or so that you've given me. So apologies if I miss your favorite physics topic. I'm going to focus on our understanding of the initial and freeze out conditions that are created in these collisions. Where are we in determining in the equation of state and the search for the critical point? What have we understood about the emitting sources? Our attempts to look for the initial electromagnetic field that should be there, but is hiding from us quite well. And then how are we leading towards our understanding of partonic energy loss, even at these lower energies? So for those of you not in the US, I just want to point out that the NSAC long-range plan for 2023 was released last week. This outlays what we've done in the past decade and where we hope to go in the next decade. It's important for funding for nuclear physics in the plan highlighted as one of the successes of the QCD physics, the beam energy scan, and what we have learned so far, that there's evidence for it being a smooth crossover at very high energies at top RHIC and at the LHC, and that it seems clear that the critical point, if it does exist, must be between 3 and 20 GeV. At 3 GeV, we have very strong indications, as you all well know, that it's dominated by hadronic physics. And then at 20 GeV, we have strong evidence of partonic degrees of freedom. So somewhere in between, hopefully, is where the critical point is. And theory is really helping us pin down that. What I think was also critical is in the future outlooks and what facilities there are. One of the emphasis is the US participation in the CBM experiment at FAIR, which will allow the US nuclear physics program to build on its successful exploration of the phase diagram started at RHIC or going on at RHIC, which was one of the things that we were pushing for to be allowed to do. And it's great to see it there. If you're not in the long range plan called out, the probability that you can get funding is significantly lowered. So congratulations to those who are lobbying hard that we continue doing this, as RHIC will be shutting down in the next couple of years. So the chances of there being any new BES data from RHIC are basically zero at this point, although never say never, but it's very close to zero, I would say. So moving on, this is well known, but worth highlighting again, because it's important for the physics that we can do. To get to the beam energy scan 2, one of the big differences from the initial beam energy scan we did was that we had significant upgrades, which increased our low PT coverage and our rapidity coverage around mid-rapidity, but to much wider ranges, and also putting in enhanced TOF so that we could do better PID, and having the EPD, the event plane detector, at forward angles to help decouple where the event plane and where the events are being taken. This is well known, but again, it's emphasizing, and you'll see the power of these upgrades as we go through these results. We have a huge number of events taken, much more than we initially proposed back in the long-range plan of 2015. The FXT was a dream with STAR, but it was not yet really formally part of the beam energy scan program. And as you can see, we took 7 energies or 8, depending on whether you count the 54 GeV taken a bit earlier as beam energy scan or not. It's part of an energy scan, so I'll count it. So we have 8 energies in collider mode, and we took 12 in fixed target mode from 3 to 13 GeV square root S. And because of the successes of the electron cooling that was put into the RHIC ring and just the work of the CAD, we managed to achieve our goal, which allowed us to get the statistics about 10 times more in all cases, as you see over here on the left. Note this is a log scale of getting about 4 times the average luminosity compared to what was managed in BES-I. And it was already an impressive feat in BES-I. And whilst we as an audience here are focused on the beam energy scan, I want to highlight that we have all different types of sizes that we can fold into this study of what are the initial conditions needed to make a QGP and how does it evolve from uranium through the isobars, which again were not even discussed in the previous long-range plan and has now been taken and since analyzed, and then significant results are coming out of that. We have the smaller systems, the oxygen we managed to do because the beam energy scan went so well. We squeezed in to the end of one of the runs. And then we have the asymmetric small systems to see what happens there. So there's a wealth of data, and virtually all of this, if not all of this, is now produced by STAR and under active analysis by our collaborators. So the critical point search, what everybody is looking for. Well, we didn't have an update at Quark Matter, so of course you're not going to hear an update on this from me here. We don't yet have one on the net proton fluctuations from the beam energy scan 2. The data is being actively analyzed as fast as we can do it. There are no major issues that have currently been identified. We are just being careful, and rightly so, to make sure that these results, when we release them, are correct. You know from history that this is a very complicated analysis that really cares about the details and very small details. So we're aiming for direct to publication release of these results. There won't be a preliminary result as the collaborations call it, but hopefully they're coming soon. As I said, you know, we worked hard to try and get them out for Quark Matter, didn't quite make it, but they should be coming soon. And like, as we said, no problems have been seen. So don't take anything in a negative from it not being released. But there were at Quark Matter a lot of updates from theory. I guess now we know that the QCD critical point is disfavored from mu b over t less than 3. So we're moving across the phase diagram of where it can possibly be. And if you, those of you that know this in detail, see that the critical point in our cartoon has moved over more into the RHIC FXT region than in our RHIC collider mode, as this range of disclosure is moved over. So there's still a hope. There's significant progress was reported at Quark Matter by several people on extrapolating off of mu b equals 0 axis. We know that that's really hard. And we seem to be honing in on the critical point value being around a temperature of 90 and a mu b of 500 to 600 MeV, which puts us again slap bang in the middle of where the FXT data set is. But we also have to bear in mind there is still not direct evidence that the critical point actually exists. Some calculations say that maybe there isn't one at all. So the experimental search really needs to continue to home in experimentally as theory tries to do these very difficult calculations. So what do we know about the initial and freeze out conditions? As I said, you know, earlier, the upgrades allowed us to have a very impressive rapidity distribution from the iTPC upgrade. And you see that in full display here. I'm showing you for 19 and 14 GeV. Here we have the lambda, anti-lambda, Xi, anti-Xi, and K0 short distributions over all of their rapidity range. And what you see here is the clear contribution of stopping as we drop down into these energies, because you see a marked difference between, let's say, the lambda and the anti-lambda. So the produced versus the somewhat coming from the stopping distributions, they get much broader for the baryons versus the anti-baryons. And the K0 shorts, the mesons, again, the produced particles are much more Gaussian. So we can really see stopping occurring at all of these energies. And that allows us to, because we have these rapidity range, to now, instead of just working out what the chemical and baryochemical potential are at the mid-rapidity, we can do it now in rapidity slices because of the high statistics and the range that we have. And you see that on display here for the 27 GeV data sets, that as we slice it, so the red is in a slice of 0 to 0.05, then we go from 0.25 to 0.45, and then up to almost 1 in rapidity. You see the chemical freeze-out temperature stays roughly the same. For the rapidity slices, we see some variation in the centralities, but note this is quite a small scale difference. But where we see the difference as expected is as you go to larger rapidities, you see that you're at a larger chemical potential. So we are seeing the three-dimensional matter that's inside of the source. And I think it'll be interesting to do, and this is analysis that we're going to try and attempt, is to try and see, do the initial conditions at forward rapidities, if you go to higher rapidity and pick a chemical potential, you can, there is a place where you can map that chemical potential to the mid-rapidity region. And do we see other differences in the kinematics that there? Can we see it imprinted elsewhere that the initial conditions were different between these two collisions, even though in the range we're looking, the chemical potential and potentially the freeze-out temperature are the same. They probably come from different initial temperatures. And I think that will be a very informative study that will be coming soon. Going back to the baryon stopping, here you see it very clearly at the 3 GeV, changing our centrality from the most central to the most peripheral. You see that the proton rapidity distribution, that's what's on display here, the peaks start to shift away from mid-rapidity, and you see sort of the beam stopping happening at slightly larger rapidity. And from that, you can work out what the stopping is by looking at delta Y, the shift of the participant proton peak away from mid-rapidity. And that's what you see here. So the calculation of the shift away from beam as a function of the centrality. So this is the most central data, and this is the peripheral data. And you see that you have an average loss of 0.19 units of rapidity per nucleon-nucleon collision. So there really sort of seems to be how the stopping is coming through is clearly on display again here.
Helen, Jorgen had a question, slide 9 about the chemical freeze-out.
Mm-hmm. Yeah,
the question Go ahead,
is the decrease in TChem with N part considered significant, or is it claimed to be flat? Depends on the correlation between the arrows.
Right.
On the left side.
The correlation, there is, I mean, these are different sides, so they're independent in that sense, but I think a lot of the errors are actually highly correlated because they come from our extrapolation of our yields and the assumptions of our tracking efficiency. And
in which case the decrease is significant.
Starting to be significant, yeah. As we go down to these very low.
No, on the left side, yes, but on the right, also towards high end part, it goes down. That's my. On the left side, it's clear that is not unexpected, but that it peaks around end part 100 is sort of unusual, isn't it?
Yeah. I mean, for one, I think they're pretty similar. Yeah, it's a good point. We should look into that into more detail and peel apart the correlation, exactly as you're saying.
Yeah, I suggest we come back later. Yeah, on this. Okay, move on, please.
Right. So that was looking into sort of the chemical. It's good that Jorgen got me back. Was looking at the chemical, but what about the initial temperature? Are there ways we can get to that rather than when the hadronization chemical freeze out occurs? And to do that, we've been looking at the dileptons. And here you see a result from Hardy's, where they look at the dilepton mass, the flow function of the dilepton mass, the elliptic flow here. And you see around where there's a big contamination from the pi zeros, you see a significant V2. It's negative because of the very low square root S. That's very expected. But as we go to higher dilepton masses, you start to see, again with large errors, but I think that's still suggestive, that because the dileptons don't interact with the medium, they're penetrating probes, they shouldn't collect up partonic or hadronic collectivity, and that's what we see, which gives us hope that indeed this is a penetrating probe with no collective boost. We've seen the photons have a shift, and that allows us to then look into the temperature there. We can look at the low mass region where you would expect the temperature to be at the hadronization, the chemical freeze out, and indeed that's what we see. It maps nicely onto the chemical temperature fits that we get. But if you look at the intermediate to high mass range, you get a temperature that's closer to the initial one. And you see indeed, and the regions where we do it, so this is mu-B, so this is higher energies and these are lower energies, we see that we get up to about 300 MeV in temperature from the initial one. But it gets harder and harder to do these, especially at the low square root S. So it would be interesting to try and see, are there other ways we can get at them? We're doing a large attempt here with the star. There's still some hope. The chemical temperature starts to peel off of where we see the phase transition occurring because the hadronic interactions become important. Still looking at the dielectron mass, we can look at the low mass excess, and here you see the low mass excess normalized by the pion yield, and we understand that there's the higher square root S, and where we were looking for the beam energy scan, there was no clear square root S dependence. And the excess was well described by in medium row modifications and QGP emission. But we know now, adding in the new BES-II data and also adding in the Hardy's data, that once we get below a square root S of about 10 GeV, we see that this excess rapidly starts to fall off. This happens in about the same place where we see the freeze out temperatures rapidly starting to drop. And we see the baryon density rapidly starting to increase. And we know that both of these effects, the initial temperature and the baryon density, affect our low mass excess vision. So this is all an intertwined and takes probably more theory effort to actually determine exactly which of these is dominating and how do we do these. And disentangle all the different effects. But the data are coming there, especially they're getting some nice precision that we're coming out of the beam energy scan too, of exactly how and where this drop-off happens. So again, because of our larger rapidity distribution, we can now study the rapidity dependence of, in this case, it's the anti-baryon to baryon enhancement as a function of PT. Here you see it for the anti-lambda, the K0 short. For 19 and 14 GeV, as a function of centrality, we see an increase as we go to higher centralities. But as we go to the larger rapidity, so this is a rapidity less than 0.4 on the left column, it's a rapidity of 0.5 to 1 on the right-hand column. And you see that there's a big difference between that as we go to the larger rapidity ranges, we're seeing an increase in the anti-baryon to meson ratio. So are we seeing the effects of coalescence or the fragmentation of nuclei at the higher rapidities? This is the work that's ongoing to sort of really, again, disentangle all the effects, and once again emphasizes the interest in going through a full three-dimensional sweep of the medium that we're looking at. Light and hypernuclei production are also now possible with the high statistics that we have, and here you see measurements as a function of square root S of hyperhelium 3, of hydrogen 3, sorry, and here you see it as a function of square root S. The peak is around 3 to 4 GeV, which is an interplay of the enhancement because of having baryon stopping, growing as we go down in square root S, but also we know that strangeness suppression is kicking in as we go down to these lower energies. So we see the intermingling of these two, but there's a reasonable description from theory, but you see again, this is log scales, so the difference are starting to be significant. And if we look in more detail at the deuteron to proton, the triton to proton, and the hyperhydrogen 3 to lambda ratio, you see that while the D over P is well described as a function of square root S, the other two are overestimated by about a factor of 2 or so. So it seems like our yields are not fixed at chemical freeze out, because these are predictions from thermal models, but that there's additional effects on the heavier than deuteron after chemical freeze out. There's some sort of coalescence of the particles, not of the partons, that's occurring. So keeping going and looking at the kinetic freeze out of these light nuclei, again, here you see we go from proton, deuteron, triton, helium-3 and helium-4. The yields are well described by the models of these ones. Here we're looking at sort of SMASH or UArcMD and JAM, so sort of more inclusive models than just a thermal model. And we see a very significant, because it says a function of rapidity and centrality dependence on these yields. If we then look at the kinetic freeze out, so looking into the temperature now, the slope of the PT distributions as opposed to the integrated yields, you see here our well-known distribution of the temperature versus collision energy, the beta, that we see this correlation between the kinetic freeze out and the radial flow. But at 3 GeV, we seem to see there's a difference in the trends, and that there's a difference with the protons being in the fit or adding in the heavier deuterons, and that the kinetic temperature of the deuteron seems to be higher than that extracted for the proton, but the flow, the radial flow, goes in the opposite direction. So is this a suggestion that, again, at 3 GeV, we are looking at a different equation of state to looking at the higher energies that we looked at with beam energy scan 1. Looking at hypernuclei kinematics, if we include the lambda into the mass, so replace a strange quark with a up and down quark, you see that you reduce the mean PT. That's what you see here in red for each of the hypernuclei, but the mass number scaling is preserved. The slope stays the same, at least within the uncertainties that we have, but we drop down the mean PT. If we look at this so-called S3 value, which is the ratio of the adding the hyperon into the helium-3 divided by the ratio of the lambda to proton, you see as a function of square root S, a potential decrease as you go to the lower square root S. And then we now need to disentangle. Is this an increasing feed down to the helium-3 from unstable nuclei as we have fragments left over at the very low square root S? Or is this a suppression at the lower square root S of the hypernuclei? This is something that we're still sort of figuring out how to disentangle. And then looking at the rapidity distribution here, again, sort of making the use of the statistics that we have and the range that we have, you see, as expected, the different decay channels give us a consistent distribution. That's good. And when we include coalescence into our model, so coalescence of the particles, then you start to get a reasonable description of what's seen there. So we see here that the ability to do hypernuclei is really increasing our sensitivity to exactly what is happening as the source evolves with time. And so this is really now a study with all of these yields and rapidity distributions and PT distributions over a range in square root S that we're really going to be understanding and enhancing our sensitivity to the kinematics of freeze out conditions. So what about the equation of state? I said at 3 GeV, it's looking like it's different. So this is well known. So we have our net proton, but we can look at the higher order cumulants. And from 7 GeV up, we seem to see, a rising order trend, which is the trend predicted by lattice. It seems to be that we are go through the phase transition. The trends are similar. But if we're down at 3 GeV, we see the trend goes in the other direction. And this is more in agreement with URQMD calculations. So having, again, a hadronically dominated system versus a quark-gluon plasma dominated system. And we're looking forward to filling in the gap between 3 and 7 and trying to see, can we reduce down our knowledge of where the hadronic source domination is? Looking again, do we have a sensitivity to QGP signals down at these very low square root S? We can also look at mixed correlations. So instead of looking at the net proton, looking at the correlations here between baryon and strangeness, and you can build up this so-called CBS correlation coefficient. Star to do this, we use protons, lambdas, and the charged kaons at the moment to look at the baryon and strangeness that's produced. And here you see our initial results here. Here it is for the 3 GeV data. It's in very good agreement with URQMD. Again, fitting with the hadronic interactions dominating. We see URQMD makes a good description of these data, but if you look at the individual components of this variable, it's not doing so well. When taken in the ratio, we see that we get to roughly the same, which is telling us something about the correlation between baryon number and strangeness number, but we don't quite have all the details down. At 200 GeV, we see a marked difference in the variable. It's underestimated by URQMD, but is consistent with expectations that we would have from the lattice. So sort of, again, we're going from a QGP dominated to a hadronic system and probing not just the net baryon number, but also the correlation between strangeness and baryon production as a function of square root S. If we want to know about the equation of state, we can look for the softening of the equation of state. And to do that, one way is to look for the speed of sound in the medium. Some of the predictions are that we can extract the speed of sound, or at least the speed of sound squared, by looking at the width of the rapidity distribution. And you know, we can do the rapidity distribution now. And here you see sort of our first attempts at trying to look into this. Here you see the width of the pion rapidity distribution. It is at this point fitted with a single Gaussian, but we know for mesons that's not a bad assumption at the minute. And you see indeed there's some hint of a softening of the equation of state, that the minimum around 7 GeV or so in this variable, and its correlation hopefully to the speed of sound. Maybe this is an indication of the softening of the equation of state there. I will point out that the NA61 have seen a minima in a similar place looking at their PP data. So I think it's still an open question. So are there other ways we can look for the speed of sound? And we saw this nice result at quark matter from CMS. And I think this will be something that we as a field should be chewing on about the details of this. So what they do is they say again that the speed of sound is related to the rate of change of the pressure with entropy. And then they relate this to the mean PT and the number of particles produced. I think the neat bit is they go to ultra-central events to avoid geometry fluctuations. So they say, okay, we know that this is overlapping. So the variations are what we're looking at that are not the geometry fluctuations. And if you make that assumption, the slope allows you to determine the speed of sound. And this is where they arrive at. They arrive at a very interesting place where the ultra-central data seems to be in complete agreement with the lattice calculation. Like I said, I think there's still some things to be looked at into this because, you know, the effective temperature they get comes from the mean PT over 3. That's a good approximation for the effective temperature. I'm not too sure that you can really map it onto the lattice temperature, but still it's a very thought-provoking measurement, and I think it's something that we should be poking at and trying to look better into. And maybe can it be done with the beam energy scan data? We have a large PT range that we can measure, especially with the upgrades, and we can have PID, so we can break this out into particle identification. I'm not sure we have the multiplicity range to be able to look at these lower energies at these ultra-central data, but I think it's something we should all be discussing for these to see where can we push these measurements? Can we extract the speed of sound? Do we get consistent results? And of course, there are also ideas using HBT and flow that we can get at the speed of sound. So I think that would be an interesting program to try and see consistency for all of these results across the energies that we have. We well know that we have elliptic flow and the number of constituent quarks scaling, that it works well down to 7.7. Here you see the 7.7 GeV data, and we see a very nice mapping between them. It holds slightly better for antiparticles than it does for particles. We're getting down to these precision details that we're looking at. And we see similar trends and observations for the V3. But when we drop down to here, you see it for 3.2. So you see we're pushing up slightly where the energy scaling breaks. And you see it clearly doesn't break. So 3.2 also, we see NCQ scaling, and we've also observed it failing at 3 GeV. So we're sort of pushing up where the hadron dominated region is. It's now at 3.2 GeV or below, squeezing in the range where we have a chance to even see the critical point, because we need to have the signals of the QGP there to be able to see the fluctuations. Looking at light nuclei again, we see a collective motion of the light nuclei. There's an A scaling, so here you see it as momentum divided by the mass number A, and the same on the y-axis. For 54, 27, 19.6, and 14.6, we see a very nice scaling of the V2. We also see it for the V3 and equally good scaling. When we drop down to 3 GeV, we see a reasonable scaling of V1 and V3 done with respect to the first order reaction plane. When we're at lower rapidity, so this is the center of mass rapidity in both cases, but once you get to above 0.5, you see that they're starting to break down. The hypernuclei also show a similar breaking in scaling, which is again consistent with late stage coalescence that we see the A scaling at all. But at high rapidity, there seems to be evidence once again that the nuclear fragments are becoming important, that as we head towards the beam rapidity, things become more complicated, and disentangling which parts are from the nuclear fragments and what are from the medium will become important. And I think a very interesting region to be studying. So looking into this, the V1 here, we see it as a 19.6 and 27 GeV as a function of centrality. So the most central is here, and here we see the peripheral, again with the extended data sets. We can start to look at this in finer and finer details, and not just as a function of rapidity, but also as a function of smaller centrality ones. You see a very similar answer as we change the centralities. And then if we move it to this looking instead of as a function of rapidity, but y minus the beam rapidity, we see that we collapse all of the energies at the close to the beam rapidity of this limiting fragmentation, which was something that Phobos was reporting way back when Phobos was running in the early 2000s. Mostly there, the focus was on looking at the yields, but now we see that with this limiting fragmentation is also a dynamical phenomenon, not just a yield production, but also in the kinematics of how these particles are moving. Here again, from 19.6, 27, 62 and 200 GeV, they all collapse on when you look into this sort of close to the beam rapidity and look at the delta from the beam rapidity. Again, emphasizing the importance of three-dimensional dynamics. Here we're looking at the longitudinal decorrelation of the elliptic flow, the R2. So what you do here is you measure it at positive rapidity and negative rapidity and look at the difference. If we really have a uniform medium, there would be no difference between the two sides. And what you see here is a strong signal of a decorrelation. It's even stronger for the R3 in the central data. For 27, for 20, and 54.4 GeV, the decorrelation is increasing with decreasing collision energy. So again, it's very important as we try and model and really understand these data sets that we have a full three-dimensional dynamics modeling from theory. We also saw this in the small systems where the results between Star and Phoenix are different, in most likely now that we've been doing the studies because of the different rapidity gaps that we have. It's really important. We can't just assume that it's only a two-dimensional expanding source. And it's even more important when we go down into these low energies. AMPT does predict that there will be a decorrelation. Interestingly, it predicts that it's going to be much larger than we actually observe in the data. So I think, again, we can be constraining the models here and really defining what is happening in these systems. So what about understanding the emitting sources? What can we do with that one? And here we go back to femtoscopy. It's sort of coming back onto the rise as we go down into these lower energies. And again, really knowing and having better techniques than when we were doing these when the SPS and AGS was up and running. And here you see the three-dimensional femtoscopy, the R out, the R side, and the R long, filling in with the beam energy scan data sets, comparing to URQMD. You see they do a reasonable job from URQMD in these intermediate energies, the collider energies that we have. The radii generally increase with collision energy. They decrease, as we know, with transverse mass. They're larger for pions than they are for kaons. Then we go in, and again, you see R out, R side, and R long, and also the lambda parameter, but now dropping down to the lower square root S. And I think this is, again, an interesting place that we're looking at here as a focus is on pions, that we start to see for the radii that are extracted. Interestingly, the lambda parameter is consistent across all experiments, that there's starting to be some disagreement between the Starr and Hardy's results and the E895. There's a tension emerging, which when you turn this into the volume of the source, so you see that it makes a very difference in the understanding of what is happening here. If you take the Starr and Hardy's data, you see that there's a very slowly evolving volume as a function of square root S, all the way up to the Alice data at the LHC, compared to what we saw with E895, where there seems to be an abrupt turn up in the volume as you drop down to the very low energies. This is something that's going to be looked at in more detail. We also see here, when you're looking at the Starr data, that there's a difference between looking at negative pions and looking at positive pions. There's a difference in the radii. This is expected and understood as being the difference in the Coulomb repulsions from it. So we're really going into detail here, and more particles are going to be coming out as the data analysis progresses. We can also look at correlations of unlike particles. And so here we're looking at correlations with hyperons. The proton lambda and the deuteron lambda correlations. These are allowing us to explore the hyperon interactions and also trying to probe better the hypernuclei structure. So again, we look in the same way as femtoscopy at those correlation functions, but we're trying to separate out the source size from the final state interactions. And what you can extract from these correlations of either looking at P lambda or D lambda is you can extract the spherical Gaussian source size of when they were emitted. And we see that this is around 2 to 3 Fermi, that for central data, the source size is bigger than for peripheral data, and that the source size for the emission, or the correlation source size for the P lambda, is greater than that for D lambda. These are all as expected. But now with our high statistics, again at 3 GeV, what we can see here is that we can start to separate out the different states of the source size, of the correlation between, in the case, the lambda and the deuteron, whether it's in a doublet state or a quartet state, tells us the difference between the scattering lengths as we expect. We don't have enough statistics yet to do this for the P lambda, so we only have the spin average source size. Here you can see the spin average source size here. But what we see here is an interesting and somewhat expected splitting between the quartet and the doublet state. And I want to emphasize that we have, even just for the 3 GeV, almost a factor of 10 statistics, because we took this ultra long 3 GeV run towards the end of the beam energy scan too. And so those data are there to be analyzed too. So this will really allow us to do detailed studies and maybe even start to separate out the P lambda state. So what about looking into detecting the initial electromagnetic B field that comes out? One of the first ideas or recent ideas we've had is looking at the splitting of the hyperon polarization. So the polarization of hyperons itself is very interesting, but which tells us about the vorticity of the system, and we've been looking at that as a function of square root S. But there is expected also to be a difference between the polarization of the anti-lambda compared to the lambda caused by the magnetic field, and that is what we've been trying to probe. And here you see again, as we go down to the lower square root S, we don't yet see any evidence of the magnetic field having a splitting. And this is true across the higher energies. Maybe there's a hint of a signal here from Alice, but there's no clear claim. And so from also for the isobar data, we don't see any evidence of the splitting coming out. So at 95% confidence level, we can put an upper limit on what the magnetic field can be at 19 and 27 GeV. There must be a magnetic field, so maybe it just dies away too quickly to be probed via this polarization measurement. So is there a way we can probe at earlier times? And one way the collaboration has been trying to do this is looking at the directed flow difference. So if you look at the slope of the V1 as a function of rapidity, Again, if this is imprinted at very early times, the magnetic field will have a different effect on particle versus antiparticle, pulling them apart. And so you would expect to see a difference in the directed flow signals. And the magnetic field we would expect to be largest because it's due to the participants in the most peripheral data. And that's what we see here. So in 200 GeV is red. You see there's basically no difference between the V1. And then as we go down in collision energy, we see a larger and larger difference between them, which is seen for pions, kaons, and protons as we drop down in energy and as we go to more peripheral data. So this is potentially evidence of the magnetic field that we can see. There is a different tensions between what would actually cause these signals, depending on what dominates for what particle species. We have transported versus created quarks. With the beam energy decreasing, we have an increasing crossing time. So maybe that makes the magnetic field last for longer and is why one can see the differences as a function of square root S, including the difference between the centralities increasing the magnetic field as you go from central to peripheral data. There's a lot of different effects to be disentangling, and exactly whether it's how the kinematics work is all going to be combined together. But as you can see, we have beautiful statistics, and clearly there is something happening here related to the magnetic field as we change energies and centralities. So I think this is a very optimistic result that we have of actually detecting the magnetic field, which must be there in these collisions. The other interesting result that we saw at Quark Matter that will be interesting to see, can we try and repeat as we look at our net proton results from the beam energy scan, is that the lattices told us that the susceptibilities should also be sensitive to the initial magnetic field. So as you change the magnetic field, you can change away from the baseline what the ratio of the susceptibilities is. So Alice has tried to do this, looking at the net proton as a function of centrality. And as you go to the more peripheral data, you see that there is a change in the value. They've managed to do their net proton fluctuations at much higher momenta than have been managed before. And it seems to have a momentum dependent. So the higher momentum is the one that shows the field. It's not clear, or the change, I should say, it's not clear to me yet why the high PT range should be more sensitive to the magnetic field than the lower PT range. And this is something that needs to be investigated. And it will be interesting. We have the ability, especially at Alice, to do this in PP data. So can one see there should be no magnetic field in PP collisions? So can we see this effect go away, taking some way here, looking at the PP data? This is an ongoing discussion that's done. It'll be interesting to see, can we repeat these types of measurements at RHIC, especially in the beam energy scan? And do we get a consistent interpretation of the effects of the magnetic field with these different techniques that are there?
Helen.
So my last bit.
Helen, yes. Jorgen has a question on slide 31. Jorgen, go ahead. He said,
I think you mentioned it in your comment. The particle to antiparticle ratio at low energy is much bigger than 1. Many more pi plus than pi minus, many more protons, antiprotons. So we have a clear initial state effect, participant kinematics. And that clearly will have an effect on V1. So that's the big effect. Now, if we don't know how big that is, it's probably difficult to disentangle that from the possibly much smaller effect of a magnetic field, if any, isn't it?
Yes, so that's why I think this is sort of a smoking gun for the field, but I think it is still
smoking gun for the field. Smoking gun for the field, or for the partonic, for the participant kinematics that we don't know.
Well, we can see that there's a big difference here. You would expect that we see a bigger effect of the stopping, and indeed we see that the difference goes positive for the protons versus the pions. They're very different in shape. So I think this will give us a handle on which part of those two, the transported versus the created, what is from there. So I think sort of there is, yes, you're right.
Okay.
This is
so,
not
okay.
as simple as.
Yeah, okay.
Okay.
Okay, move on, please.
Right. So just my final bit in my last few minutes is looking into understanding the energy loss in the QGP. We know at the higher points of the beam energy scan, we are seeing energy loss. This comes from the beam energy scan 1, but above 27 GeV, there's clearly a suppression. So we're seeing our traditional partonic energy loss signals above those energies. If we go to lower ones or even around there, if we're looking, we can break out from the different particle ID. So this is for charged particles. And we know that there are differences between the baryons and mesons at intermediate PT. Here you see it for 19, 27, and 39 GeV broken out for the K0, lambda, psi, omega, and phi. And you see that we have large uncertainties on the phi at these points, and there seems to be splitting. It definitely is a mass effect. But with our beam energy scan 2 data, we're able to go in and really make precision measurements of the phi. This is one of the reasons we wanted high statistics. The phi is so rare. And I think here what it was nice to look at is if you look at the 14 or 20 GeV, the red here, you see the phi goes above 1 in the RCP. And if we track our way across here and go to the 19.6, here the phi was measured before, we couldn't tell where it was. It seems to be tracking more with the lambda than it does with the kaon. So it's clearly a mass effect that we're seeing in the different enhancements or suppressions. Flow is the understood cause for this. It's pushing out at a higher PT depending on the mass. The question we need to be focusing on in these intermediate and square root S is the flow hiding any energy loss? We always sort of say our RCP is our measure, and if it goes less than 1, we see a loss or an energy loss because we expect scaling, especially of the hard processes. What exactly is a hard process becomes a little squishy down at these lower energies. But this is something we can look into. And one of the other bits we need to disentangle is the changing slopes of the both the baseline and the PP or the peripheral collisions, which we use in place of PP. How is that affecting these differences? Because as we well know, the RCP being the ratio, shifts versus drops are hard to disentangle. And this is something we need to think about. We also look at the J-psi RAA, the new data here at 14, 20, and 27 GeV. And we see it's very flat, the nuclear modification factor of the J-psi as a function of square root S. There's no strong energy dependence, at least at RHIC energies. As you go to the LHC, you see that its changes. There's a strong interplay here of dissociation, regeneration, cold nuclear matters, and the spectral shape all have to be taken into account. And you see that this is starting to happen here with the modeling of what comes from regeneration, where is the primordial. There is a stronger suppression as you go to higher energies, as you would expect. But the regeneration at the higher energies where there's just enough charm around to allow for regeneration. If you lose the J-psi at these low square root S's, the charm is just gone, and the probability that they regenerate is basically 0 at these lower energies. If we look at now as a function of n part, you see here for the different energies, the 54 GeV gold, and the other gold, and the isobar data, you see that there's a clear n part dependence or independence. If you look at the energies, again, it seems constant here. So there's more suppression at RHIC due to much less regeneration. This is what we as understood here. Again, you see the RHIC data with the LHC almost coming back to apparently no suppression because of the significant regeneration that's going on. But then my point, I think what is interesting and was again being discussed quite a lot at Quark Matter is, well, if RAA has to fold in both the suppression and also the spectral shapes, can we look instead at the shift, look at the delta PT, the energy loss, instead of taking a ratio, look at how do we have to shift the spectra to it. And this is a quick analysis that we've been doing, and I think will be take some more detailed calculations to look into. But it's very suggestive that if you calculate this shift in the PT spectrum, how do you have to shift it to the left to match the PP spectrum? as a function of the energy density created in the medium, so not as a function of square root S, but the energy density, you have to make quite some approximations to get to the energy density, building up from the dn charge d eta, looking at the overlap region using the Glauber model and so on. But if you make these approximations, you see that there's a pretty decent lineup of the correlation of the energy loss with the energy density, which is what we would expect, that the energy density is what's driving the partonic energy loss. Again, this probably needs more details of doing these, seeing what are the correlations between the uncertainties, but we see it over a large square root S from 5 down to 200 GeV. And I think it would be interesting to try and do this looking at the higher beam energy scan data sets. Is there a place where we see this drop away? We know at some point we're going to end up with effectively an energy loss that it is negative because we see the push out of the radial flow. But I think that would be interesting to go into our higher energies as we come up and see, does this correlation, is it preserved for all of our other data sets too? But we also know that for the entropy and charged particle density, making that link is very sensitive to the viscosity that we assume or is there in the medium. And at the moment, this is assumed to be constant over all of these square root S. And I think, you know, that again is a very hand-wavy discussion that's going that we could make crisper and see how well this lasts through. And that brings me to my summary, to the end of my talk. We have a wealth of results that are available now from across the whole beam energy scan 2 data sets. I couldn't cover them all, even you giving me an hour to discuss them. Many results were released at QuarkMatter, and there's much more to come. People in the collaboration are really actively looking into these, seeing across the whole wider rapidity range, really looking into the 3-dimensional kinematics of this. As these large data sets become available, I think we're going to have to start to be doing some sort of Bayesian global analyses of all these results if we're truly going to exploit the full power of the beam energy scan 2 data that we have. From Jetscape, we heard at QuarkMatter that they are now working to include beam energy scan physics into their model, building off of the work that was done by the BES collaboration and others over the past few years. This has really been a theory experimental collaboration to get the data to where it is. And we also have not just the beam energy scan data from RHIC, but also future data from CBM FAIR. Again, you heard from the long range plan that there's some encouragement of the US groups to go and join in the analyses there, take our expertise from the US there. There's also Hardy's and Shine, which of course are taking data now and producing results. And there's potential for future ones. The dileptons look very promising and are really hard to do with the star data, just the uncertainties are large. NA60 plus is a proposal at the SPS to really focus in on this. And as we really start to look to the future, the EIC is coming at RHIC. We're going to be shutting down in 2025, so we have 2 more years of data taking. And then the EIC comes. Can we put a fixed target into the EIC? We have 100 GeV nuclear beam that's going to be hitting, and a very forward focused detector that's being designed at the EIC, because it is asymmetric collisions, of course, when it's EA. So can we put a fixed target in? And then we can essentially reproduce or look in more detail at what is happening there. I think that's a very interesting program that maybe we can get behind. It's not part of the baseline EIC detector. Maybe one can put it into EPIC. We've shown that we can do fixed target analyses at RHIC without any danger to the machine or to the accelerator by putting in a permanent fixed target at the entrance to the experiments. Can we do this again at the EIC? I think that one. Or if it can't be done at EPIC, you know, there is hope for a second detector. It won't be there day one. But as we study the data that's come out of the beam energy scan, maybe this is an opportunity to sort of be able to expand on regions where we want to be able to look, or look at different beam species, so go away from being gold. I think this is something that, again, we should be talking about as the EIC detectors become fixed. The net proton fluctuations are coming soon, but I want to remind everybody that the beam energy scan physics program is much more than that, we just with the results that I've whirlwinded you through today, you see that we're really learning a lot across about the hadronic and the QGP medium as a function of square root S. And we look forward to much more discussions to come. Thank you.
Thank you very much, Helen, for this comprehensive talk and a lot of information here. We still have close to 120 participants here. So now that this talk is open for comments or questions, please raise your hand so we can call you in that order. So, any questions or comments for Helen? I don't see any hands yet. Okay, Jorgen, please go ahead.
I wanted to give somebody else a chance to ask a question, but if nobody does, if you go to slide 28, this is where you use HBT to look into strong interactions. So there you invert the normal procedure. You have to assume a source size and then get the final state interactions. Now, what we have found, as you know well at LHC, is that we have to make corrections to the source size from strong resonance decays because their lifetimes are of the order of the source sizes, a few Fermi. And if we don't do that, we don't get the right final state direction. Is that something which may also be needed, or has that been looked at the lower energies, so that you have not a Gaussian source size, but a Gaussian plus an exponential tail, where the exponential tail depends on the particle and the resonance decay which contribute to it? Has that been looked at lower energies?
So I did not the expert in this. I don't know if the person or people who are on there. I know that we assume it's a Gaussian source size at the minute. That's what is done here. And I know they're aware that, you know, looking into this and doing the feed down is important, but exactly how much the sensitivity is not sure.
The answer is yes. The resonance decay effect already folded into the analysis for both.
But it's not.
P lambda.
Okay.
And remember, at this low energy, resonance contribution is much smaller comparing to high energy.
That's true. So, but you fold it not only into the lambda parameter, but also in the shape of the source. That is a specific point.
That we do not do, because that is strongly model dependent. Be careful with that. I would put a caution there. Even you do it, yes.
Okay, but what at least at higher energies, where I agree you have more, if we don't do it, we don't get consistent results from different particles. So one should at least look into it and maybe include it in the systematic error.
Yes, but I would like to comment again on the Alice result, because Alice is doing only for PP. The effect is much stronger. On top of that, lots of more contribution. So at this energy with AA collisions, I think it's that effect is not our major concern at the moment. We have yes, we have we did systematically from PP, P lambda to D lambda. So this is really the most beautiful result in terms of final state interaction. Yeah, and you can see the negative F naught. It's actually because of the hypertriton bound state. Really beautiful. All right, any other questions or comments to Helen? Uli, please go ahead.
Yeah, Helen, thank you for this very impressive talk. I mean, it's just unbelievable how much data there is. And to me, it looks like you have just begun analyzing them. And that's what brings me to my question with RHIC shutting down in 2 years. What's the plan of STAR to ensure full analysis of these wonderful beam energy scan data? Have you thought about organizing the future?
So we have thought, yes. So the collaboration is behind analyzing the data, because I guess we should emphasize that it's RHIC shutting down, not STAR shutting down in 2025. People are very invested in getting these data. I think we saw that Phoenix have more trouble, I think, because there were S-Phoenix being built. And so, of course, the workforce was redirected. I think in this case, we do have we're optimistic about keeping our collaboration size active, because we can't all head to the LHC, much as many of us are involved. I think that there are interests there. So we have several years without taking new heavy ion data at the lower energies. Of course, the LHC is running, it's still taking data. I don't mean to say that it's not. But with FAIR not starting yet, I think people are interested in keeping this going. And this is why we've been pushing also very hard to produce the data rapidly. And it is all produced now, because we do realize that the new data is always the sexiest data, and that the collaboration will fade as longer as RHIC comes down. But there's really a push to get as much data out as we can. But you're right, at the moment, we're just tickling on the surface of it. But the collaboration is very invested in keeping this going. We have a lot of students and young postdocs who are actually doing the analyses. So that gives me confidence that these will come out, because there are students just starting their PhDs working on these data sets. So they will be pushing hard on it. So I'm confident, but it will be the community. So.
Yeah. I'm looking at this, of course, with the eyes of a phenomenologically oriented theorist. And I observe that on the theoretical side, the tools that are required for full understanding of what you have been measuring are just now being developed. I mean, fully dynamical simulations at finite baryon density with all the diffusion currents included is not easy to implement, and dynamical studies, I mean, how the fluctuations are affected by the dynamics of the collision is a complicated issue that we are just beginning to get our hands on. And it would be a shame if the people doing experimental analysis had shifted their interest to other areas by the time these tools become mature and can be applied to these wonderful data that you have now.
Yeah, just following Helen's comment, Uli. So in STAR, we have quite a number of groups who are interested in complete this data analysis, and at the same time also interested in CBM program. So in that sense, the collaboration to complete BES-II data analysis, to me, is secured for most of these observables Helen presented. Yes.
And I guess the other point that recently, over the past few years, we've had quite a few groups join STAR, which for experiment that it has a shutdown date, I thought is very optimistic. And people are joining because of the beam energy scan data. They're not so much joining because of the AAPP data, though there are very interested people in those. But so I think that also that people really want to get their hands on this beam energy scan data. And the more we show, the more people want to look at these. I think, as you say, we're just getting there, and the theory is getting there to be able to really do detailed. But I agree, you know, this is something we will have to keep pushing as a community to make sure it doesn't get lost, which would be tragic.
Yeah, thank you. That's very good to hear. Yeah,
Jorgen had a comment about this feed down for this. I call it the baryon correlation.
You don't have to come back to it. I hear just that was a comment more to you.
Yes, I also agree with you. Yes, so
okay.
we will take care of that part. Any other questions or comments? If not, I would like to go back to page 7. Yep. Page 9. I'm sorry. Where Jorgen raised the question about this chemical freeze-out temperature centrality dependence. This actually, personally, I also found a little bit odd on the left plot. So I just want to come. I don't have answer at the moment because this is a chemical freeze-out, not the kinetic. Kinetic we know because the bigger the system is, cooler. But here, I think we need to look into it. That's the only comment I have. This is, yeah, I already at Quark Matter noticed this dependence. Jorgen, you want to comment on this? You raised your hand, Jorgen.
Yeah, no, I not on this because I have the same question as you, because chemical, I mean, that it goes down at low end part, one could possibly relate the fact that it goes down at low square root of S. Not clear how, but at least that could be connected. But that it goes down towards more central is surprising. So maybe it is indeed not significant, but it would be nice to follow that up a little bit.
Yeah, and
Yeah,
I
I
think we need to look a little more into the different particle species that go into the fit.
Yep.
Yes, I also look into how these parameters are extracted. There are quite few models approaches on the market, so I don't remember this one specifically. So.
What are the prospects for reducing the error bars for the left plot to the extent that you can distinguish between tendencies in different rapidity bins?
So I think that's where Jürgen had the good point, and this is, we haven't taken out the correlations between them, so I think that will help. So it doesn't reduce them, but for looking at the trends between them, because like I suspect a large part of these uncertainties do come from the extrapolation to full PT and the uncertainties due to our tracking efficiency, which will be highly correlated across these rapidity gaps. So I think that's where we need to put some more thought into, and instead of indicating them as one error band, putting them as which ones are correlated and uncorrelated. So then that will help.
Okay, thank you for the questions and comments. Any other questions or comments for Helen?
Well, I mean, just a comment on thinking more about this left plot here. As you go, the right plot shows that as you go up in part, as you become more central, the baryon chemical potential increases. And if the chemical freeze out happens on the hadronization curve, larger chemical potential comes with lower temperature. Are you speaking?
No, I'm not speaking. We had internal discussions. I don't want to go to public here. So I have for this plot, yes, we had because before quark matter we start always. I think it's very good tradition. Have a few days of go through all these talks. Yeah, so I think we need look into detail on this. So this is interesting.
Yeah, I had one more comment on a different point on slide 21, where you show the CMS results, which indeed very provokingly said, could we do that at the beam energy scan? So a question of warning. The warning is those who remember NA38 results on J-psi when they went into the tail of the distribution. If one bins finer than the actual impact parameter resolution, you get all kinds of weird biases. Now, and we looked into the impact parameter resolution at very high energy. We have many particles. It can be of the order of a few percent, 5–7%. So that's probably not a problem for CMS. But if you would want to do that at the beam energy scan, you would have really to make sure that your resolution, not on n-charged, you can have an n-charged resolution of 1 if you count every particle, but on the impact parameter, so that your n-charge is correlated with the physical quantity. That may not be so easy at low energies just because you don't have enough particles. You neither need maybe with a very large phase space, it's possible. But the first thing when you do this fine binning at the tail, make sure you have a physics resolution on what you bin, and not otherwise you start biasing fluctuations. And that's my second question, but that I was not at quark matter. Was that discussed whether there could be a bias, for example, a slight increase, because you're on the steep falling tail of the around B = 0. And so very small dynamical biases could create that, for example, a slight increase in the number of jets. Has that been discussed at quark matter, or is that being discussed in the CMS paper? I mean, bias questions are always very tricky around the knee.
Right. So I'm not a member of CMS, but I agree. I mean, part of their point was that you go away from that you are looking at fluctuations, not looking at geometry, that you basically have as close to b equals 0 as you can possibly get. So you've got rid of the geometry, was their argumentation. Now, what drives these fluctuations then in the multiplicity? I mean, you're right, maybe it's excessive jet production, which ticks it up, because I think even there, they're starting to look at few particle differences in them. So that was part of the discussion of what really you're doing. So I think everybody took this with a sort of, it's interesting, needs to be sort of looked at in more detail of what exactly is, just as a provocative result. I think, you know, it's an interesting idea that it fits so neatly.
Zhao Chen, are you same question on this slide or different one?
The same. Actually, just a comment. So
okay, go ahead.
Helen mentioned under fluctuations in the ultracentric. Here we are not looking at the fluctuation on the impact parameter. Instead, we are more looking at the fluctuations on the energy density or the entropy.
Yeah, but that's what you claim. So people still worry about the geometry fluctuation. That's what the comments about. I think
or a bias on the dynamics. If you just increase slightly the number in the tail, the number of high PT jets by a very small amount, this is a very small, then you would get a small increase in the average PT. So if you would go, I
think it's a good valid comment. Yes, and I also have a comment and suggestion to RHC people. You see, if we're trying to avoid this geometrical fluctuation, do it with the proton-proton collisions at 13 TeV. You have billions of events. There you have no such geometrical fluctuation. Of course, the jet effect is still there. But I think to PP high multiplicity, this will be a good check. Right?
Yes.
Proton-proton collisions at 13 TeV. You have billions of data.
Yes, we could look at, one should look into that, yes.
Yeah. Very good. Any other questions or comments? I still see Jorgen's hand up there, so I guess that's all the question. Okay, so I don't see any. So thank you once again, Helen, for this nice talk. And thank you very much. And thank you all for participating today's discussion and seminar. So next one will be October 24 at the same time. Goodbye. Oh, Yi, do you have any comments or questions or suggestions?
No, at this point, I think.
Okay, then that end of the seminar. Thank you, Helen, again. Thank you all.